Hey guys, it's Mr. Sheeline here. I just want to go over some things that maybe I didn't make terribly clear in the notes the day before. So this is just for anybody who wasn't able to be at the in-class lecture. I guess as of right now, this would be the in-class lecture that you would have gotten on Thursday, October 8th of 2020. So again, this is something I missed in the notes. I didn't, I guess, fully grasp that I missed. So I'll try to keep this as brief as possible. But for the most part, this is what I missed. So in the notes, remember I talked about, ions and isotopes. We talked about all that good stuff. For the most part, breezing past, the atomic structure, specific atomic structure of an atom. The fact that it's made up of protons and neutrons and electrons, because we should know that. And we should know the charges that they have. Electrons are negatively charged, protons are positively charged, neutrons are neutrally charged. Okay. So, what was it that I missed? Well, what I missed was talking a bit more broadly about or more specifically, I should say, talk more specifically about ions. So remember, ions are, they're elements that have a different number of electrons. So something I didn't make clear was the ability that we could have, or the ability we have to know the number of electrons that a given element has based upon its, information in the periodic table. So here is a periodic table, and this is going to be the periodic table you guys are going to be using pretty much for the rest of the year. But we're going to use this as a way to show how it is, or show you guys how you can know the number of electrons in a given element here on the periodic table. So let's take a look at it. Okay, so taking a look here, okay, we have all of these lovely elements all span across. And something I did talk about in the notes was the differentiation between this number and this number and this thing. So as a recap, remember, so the 5 here on boron, okay, that is its atomic number, okay? So that's the atomic number. The 10.8111, that is its atomic mass, okay? So there isn't anything in here specifically talking about the electron. But we can figure out the number of electrons in this boron example here by looking at this. So all of the elements, for the most part, when they're represented in this way on the periodic table, they're in their most stable state. They are neutrally charged, relatively speaking. They're not ions, is more or less what I'm saying. They're not ions, so meaning they do not have a different number of electrons. Well, we know, though, that they are at some sort of neutral state. So because they're at a neutral state, that must tell us then that they have an equal balance between their electrons and their protons. So if they have an equal balance between them, that must mean then that the number of protons must equal the number of electrons. So if boron has an atomic number of 5, that means boron has 5 protons. And if it's neutrally charged here, it's not negatively charged or positively charged. That must mean then the protons must balance out with the electrons, and we must have then 5 electrons. Electrons. Okay. Because again, that would balance out the charge on our element here. Okay. Now, and that's what makes something an ion or something not an ion. So let's say that boron loses, we'll say, 1 electron. So if it loses an electron, all of a sudden now we've got boron and then 1 plus. Okay, means it's lost an electron. If it gained an electron, this is lost electron. If it gained an electron, then it would be B1 negative. Okay. And so on and so on. It would be if it lost 2, then it would be 2 plus. If it lost 3, it'd be 2 or 3 plus, and same difference on this side, just to be negative. So we can use this to see, use the periodic table to see the number of electrons. So for instance, silicon here has 14 protons, and we know that because of the atomic number is 14, okay? So it has 14 electrons. Arsenic has 33 protons, so it has 33 electrons. Bismuth has 83 protons, so it has 83 electrons. Radon has 86 protons, so it has 86 electrons. Helium has two protons, so it has 2 electrons. I think you get the idea now. So this is how we can use the periodic table to tell us the number of electrons something has, so that when we see, or so that then we know, oh, if we see B1 plus, oh, well, that means that it lost an electron. So instead of having 5 electrons, okay, that would mean then that this B1 plus has 4 electrons. And in the opposite way, if we see that it gained an electron, so it would be 1 minus, it wouldn't have 5 anymore, it would be 6 electrons. Okay? Hopefully we get that idea. If you still don't get that idea, it's fine. Maybe send a chat to me because it's that easy. And then one more thing, just to talk about, generally speaking, talking about this periodic table. So the periodic table here is a reference that we use chemistry for a number of different things. I just want to briefly mention how it is that we get these numbers for the atomic mass. So just a quick little what's it called? Just a quick little diddly about it. How do we get, say, for manganese, how is it that we get the 54.938505? Okay, how do we get that? Well, more or less, this is how we get it. It's the fact that the world is composed of elements, and there's different kinds of elements, and within those different kinds of elements have different types of their own selves. So, for instance, I don't know off the top of my head the number that boron has or that manganese has, but they both have a different number of isotopes. And remember, isotopes are nothing more than just elements with different number of neutrons in its nucleus. So however many either one of these guys has, and for that matter, any of them here on the periodic table, they have a different number of neutrons, which then means it has a different mass. Because remember, one neutron is 1 AMU, one proton is 1 AMU. So if you lose, give or take, you lose a couple of neutrons, which is possible, then you may lose an electron or two, you may have a different mass at a different point in time. Different isotopes have different masses. And so what scientists do then to find the atomic mass, pretty much all you need to know what they do is they do this. So let's use hydrogen as an example. So hydrogen has, we'll say that hydrogen, as an example, has 2 different kinds of isotopes. Let's say we've got hydrogen 1 and we've got hydrogen 2. Now, for hydrogen 1, now again, this is off the top of my head, but let's just say for the sake of argument, hydrogen 1, like if you were to go out and pick like 100, if you were to go out and you were able to pick 100 atoms of hydrogen, 98% of them, so 98 of them, are going to be hydrogen 1. Whereas hydrogen 2 is roughly about 2. So you would, out of that 100, 2 of them would be left, on average, 2 of them that would be left over would be these hydrogen 2 atoms. Now, why do we need to know the percentages here? Well, the percentages go in towards the average. So more or less what scientists did to figure this number, they saw the number of isotopes, they saw the number of hydrogen 1 isotopes floating around and saw, oh, wow, there's a lot of them. Well, that means that on average, okay, basing the, or sorry, per capita, I guess in this case, that because there's only 2% here and there's 98% here, insert complicated formula here, they found the average between the two of the masses based upon how much there was in the world. So just, because that there's so much more hydrogen 1, the mass of hydrogen in general is going to be closer to the mass of hydrogen 1, okay? Which I know that seems kind of weird. Maybe we're still not understanding that. But I hope that's as clear as I can be without having to bust out the equation and have you, actually find the average mass due to its abundance. Because I tried that last year. It didn't work out too great. But anyway, again, what you need to know is that different isotopes, the different types of atoms, elements that have differing numbers of neutrons, we use those, all the different types of isotopes, to find the average atomic mass, give or take. So, and you'll be working on that on the PhET online lab, doing that. So that's pretty much it. Hopefully this maybe helped you on a worksheet or two where something may not have made sense. So if you didn't get, if you've already forgotten all this stuff over here, what I did over here, maybe rewind and go back to that and check that out again. If you still have any questions, guys, let me know. If not, then I'll see you in the next one.